This is a lecture on those 4 theorems that are used to prove the existence of roots of polynomials. This is a lecture from Math 107 in Chapter 3. Recall from the previous lecture that we've been saying if a polynomial is of degree n, it has n roots. And although it looked graphically that like this might be true, we need to do a little bit better. We need to try to prove that that statement is true. And for that purpose, we have 4 theorems. Well, we have 7 here I'm listing, but the first 4 have to do with the existence of those roots. And they are the remainder theorem, the factor theorem, the fundamental theorem of algebra, and the polynomial factorization theorem. And those are the 4 theorems we're going to go over now. And what we're trying to do is prove that the roots exist. As I said before, it's not trivial to find roots of polynomials. And you certainly wouldn't want to go to looking for something if they don't even exist. So it's better to know that at least the roots exist if you're going to spend all the time looking for them. So we're starting out with the remainder theorem. This might not look like much. In fact, it might just be a way, you might see it just as a way to rewrite the polynomial. Consider that I have some number such as, say, 37, and I divide it by 5. Well, then I'll get 7, and I'd have a remainder of 2. So I could write this in a different form. I could write 37 equals 5 times 7 plus 2, and that's true. You see how I rearranged it? If I do polynomial division, I can do the same kind of rearranging. So I'm using examples that are on the lecture notes so that you might not have to take too many notes. Okay, say I have this polynomial that is, which one I'm going to use? 3x squared, that's an equal sign, minus 11x plus 25. And I'm going to divide it by x minus 2. This will also be a refresher for polynomial division. So for polynomial division, I look at the leading term here in the divisor, and I look at the leading term that I'm trying to divide into. Of course, that's going to change as we go through the problem. And I say, what would it take to change x into 3x squared? Well, by multiplication. If I multiplied by 3x, that would work. So when I get my first idea of what number to put up here, I ignore the negative 2. I look only at the first term. But when I carry out the multiplication, I have to do the whole problem. So I go 3x times x gives me 3x squared. Then 3 times minus 2 gives me minus 6, or 3x times 2 gives me minus 6x. Okay, did you see what I did? I took the leading term, figured out what I needed to turn the x into 3x squared, and I put that up on top as part of the answer, as the start of my answer anyway. But when I go to actually make this line, I have to multiply everything, the x and the minus 2. So I've got this line. Now this is a subtraction problem. You can try to change signs here, but I don't do it because then I end up second guessing myself and wondering if I really did change a sign and maybe I should change it back and did it. So it becomes too complicated. It's better to do it in your head. So say you have 3x squared minus 3x squared, that's 0. That was your plan, that was your design. The next term, minus 11x minus a negative 6x. Well, minus a negative 6x is like adding it to the negative 11, so I'll have minus 5x plus 25. Bring down the next term. Okay, that's one place where you're going to make your errors in that subtraction. Now I repeat the process I did before. I say, what will turn the x into minus 5x? By multiplication. If I multiplied by minus 5, that would do it. So I put the minus 5 up here. But then I carry out the entire problem when I multiply. Minus 5 times x gives me minus 5x. Well, that was the plan. Minus 5 times minus 2 is a plus 10. I'm subtracting the 5x terms go away, and I have 25 minus 10, which gives me 15. At this point, I stop, because to turn x into 15, I would have to multiply by 1 over x. Well, then I've got problems, all kind of problems with division by 0. At any rate, that's where you stop. Now, I'm going to write this using that remainder. So let's start off here. I would have to write that 3x squared minus 11x plus 25 is equal to x minus 2, I got that from here, times the answer that I had up here, 3x minus 5, and then I'd have to add in the remainder of 15. Okay. Here's another example. So just help in case you have, need a review on polynomial division. We'll use 3x cubed minus 5x squared plus 3x, maybe minus 10. Okay, and I'm going to divide by x minus 1. So I put the x minus 1 here, and I divide. Here's 3x cubed minus 5x squared plus 3x minus 10. X into the 3x cubed, what will turn x into 3x cubed? It will be multiplication by 3x squared. So now I carry out the multiplication, and I get 3x cubed minus 3x squared. And then I subtract. The first term goes away as planned, and now I have minus 5x minus a negative 3x, so that gives me minus 2x squared plus 3x. And I ask the question again, what would turn x into negative 2x squared? It'd be multiplication by minus 2x. So I get negative 2x squared plus 2x, looks like. Alright, the first terms go away, and now I have 3x minus 2x, which is x minus 10. Well, we'll turn x into x. Well, that's just multiplication by 1 would do that to create that line. So I have x minus 1. Again, I'm subtracting, so this negative 10 minus a negative 1 will give me minus 9. So I have a remainder of negative 9. And I could write this in the following form. 3x cubed minus 5x squared plus 3x minus 10 equals, and I will put the x minus 1. It's as though I factored out x minus 1, and that's sort of where we're going with this. 3x squared minus 2x plus 1 minus that 9, which is the remainder. Okay, now that you understand how to put the remainder in and to write the function like that, now we come to the next theorem, which states that if, say I have a polynomial and I divide it by x minus some number, and I'm going to call it r for a reason, but when I divide it by this, remember this r is just going to be a number, and if the remainder is 0, then this r is a root. And remember, if something's a root, if you evaluated the polynomial at r, you would get 0. So when you do the long division and the remainder is 0, this tells you that the number here is a root. Right. So when we had the two examples from before, we divided, whoops, don't have a pen, we divided the 3x squared minus 11x plus 25, and we divided it by x minus 2. In this case, we got another polynomial. There's 3x minus 5. That's right. Okay, and we had a remainder of 15. Because we have a remainder that's not 0, this 2 is not a root of the polynomial. Okay. So now let's try one where we do have a remainder 0, and I'll show you how that works. So here's our polynomial. There might be a sign error in the notes, but let's just look at this. X squared minus 6x minus 16, and we're going to divide by x minus 8. We want to check out to see if x of 8, if 8 is a root. So I divide here, and I will have x squared minus 6x minus 16. So what turns x into x squared? It's an x. So I've got x squared minus 8x. Now I'm subtracting. Minus 6 plus 8 gives me 2x minus 16. What turns x into 2x? Well, it's a 2. So I get 2x minus 16. The remainder is 0. So x is a root. Now, or 8 is a root. So that means I could write x squared minus 6x minus 16 equals x minus 8, and then times x plus 2, and then 0 remainder. So actually now I know both roots because things simplified. I want to show you what that looks like in terms of in more general terms. So remember, that's how I wrote that. So what I did was I took p of x and I divided it by x minus whatever I thought the root might be. Okay. When I divided out, I got an answer up here. This answer is also a polynomial. And there may or may not be a remainder. Let's say that the remainder is equal to 0. So when I write the polynomial in this start of a factored form, I have x minus r times q of x. Now, whatever the degree of p was, let's say this was a degree n, the degree of q is n minus 1. It's an easier polynomial than p of x. So I have factored out one of the roots. Now to see that that truly is 0, let's say that r is a root. If r is a root, then p of r is equal to 0. So this would give you, that means x is r, so I've got r minus r times q of x, q of r. It doesn't matter what this term is, r minus r is 0, and that truly makes everything 0. Now that you know how to write the polynomial in terms of r, so if you knew a root of the polynomial, you would write it as x minus r. Let's say this is the first root, and then you would have some simpler polynomial here. Okay. The fundamental theorem of algebra states that every polynomial has at least one root. So if it has at least one root, say I could find it, I could write the polynomial like this. Well, now we're going to go immediately to the polynomial factorization theorem. What is q of x? It's a polynomial. So the fundamental theorem of algebra says q of x has a root. Okay, so I could write this and pull out the one root that I know on q, and I would have x minus the second root, but q of x now with division would become something similar. I'll call it s of x. But this is also a polynomial, so the fundamental theorem of calculus says s has a root. So when I pull out its root and factor that one out, then I would have, I'll have to call it R3 to keep it straight from the others, then I would have another polynomial. And I can keep going like this. And when do I stop? I stop when this polynomial, which is getting simpler and simpler, 1 degree at a time. So if this was a polynomial 6, a degree 6, this would be a 5, this would be of degree 4, this would be of degree 3, and I would keep working down until the last thing I would be left with would be the leading coefficient. It would just be a number, and there would be no variable and nothing to factor. You'd have to keep going, and then the last term you have would be that leading term, which is it's not going to go there, so I have to put it up here, a to the n. And there's your polynomial factorization theorem. So any polynomial, it turns out, will have, how many times can you do this? You can do it until you're to a to the n. That means you would factor out n roots. And those are the first theorems. They're the theorems showing the existence of the n roots of a polynomial of degree n. Remember, the R1 and R2 and R3 do not have to be different numbers, distinct numbers. They could be the same, in which case you would have a multiplicity involved with one of the roots. Also, they could be complex. But if they're complex, let's say R1 is a complex number, 3 plus 7i, then R2 or one of the other roots would have to be its complex conjugate. So there's some rules of what you would get.